Our graph is very different than those graphs, so that makes our algorithm novel and slightly it is interesting. So in this graph, we use maps between shape extremities as the graph vertices, and each consecutive columns of vertices are completely connected by edges, and there is no weighting going on these edges. And as I told you, weighting is a little bit problematic. You need some initial maps or some other heuristics to put those numbers. We are avoiding that, so we don't have any weights. And then the problem reduces to optimal path finding on this graph. In this example, the red path is our optimal path, so I am outputting the nodes or the maps on this red path as my result. And note that since this is a path, it implies other maps between non-consecutive pairs consistently, so we are making the set of maps consistent naturally. So yes, and the process includes accumulation and usage of isometric distortion information on the program paths with dynamic programming tables. And let's see the algorithm in detail for 1 minute. Assume I am given these shapes S1 to Sm, and let's construct the graph. For that, I am enumerating maps between each consecutive shape. So let's start. This is my first graph vertex. This is another map. Note that it is a different permutation on the feed, please. Then another. So like this, as you understand the flow. We build our vertices this way. Then the interesting part begins. We create paths PRM from S1 to Sn plus 1 and store their overall isometric distortions in this calligraphic D in the dynamic programming table. So for n equal to 1, it is not quite interesting actually. There will be R paths and each path will be of size 1. So there will be just one map in each path. So, and the overall distortion will be again very trivial. It will be the isometric distortion of this map. So this is the first overall distortion, second, and so on. And things get interesting when the new shape comes. So I have R newcomer vertices here, maps in other words. So my task is to introduce these vertices to my system. So I pick the first newcomer and create paths ending at that vertex. And each of these paths have overall isometric distortion, and I store it in the dynamic programming table for later access. And I also emphasize the best map among these guys, the minimum distortion one. I do it for this, and I emphasize the best one. Do it for this, and emphasize the best. Next shape comes. So here, interesting thing to observe is the paths can change in this process. So the subpath coming to this guy, for instance, changes as you can see. So this is the beauty of dynamic programming. As you know, you look the problem from a global point of view, and you can change your decisions on the way, unlike a greedy algorithm where you get stuck with the same decision at all times. So anyway, so we have R newcomers and R new paths like this, and again for these R newcomers, I have R new paths with their new distortions, and for the final guy, I again have R newcomers, and I have R new paths ending at these newcomers. And since we are done, now I have these emphasized distortions, and I pick the one with the minimum distortion. So this is my result basically, and the nodes or the maps on this path are announced as results. And speaking of results, here are some the extremity matching on the Shape dataset. And during the computation of our isometric distortion function, we are automatically finding denser maps like 300 by 300 maps, and we interpolate them to full dense maps with well-known techniques. So what I am trying to say is you can also do full dense mapping with this algorithm, not only coarse mapping. And in the comparison with the state of the art from Stanford, we see that they suffer from the blended intrinsic maps initialization, especially on the noisy dataset. We, on the other hand, do not require any type of initialization. We just go and explicitly minimize stuff, so we don't suffer from it. But if the shapes are not noisy, then we are as good as them. So there are only advantages in the case of noise. As far as the timing, we are faster than them because we don't need any initialization, but they require dense initialization. And as far as the future work, we have used a simple map enumeration based on combinatorial tricks. So it's the combinatorial enumeration. We have worked on the permutations. One can think of better or different enumerations which will enable partial isometric matching, non-isometric matching, and as well as full dense matching without interpolation. And another future work can be finding new ways of combining maps. And in conclusion, rather than improving a given set of initial pairwise maps, we go and explicitly minimize the overall isometric distortion. And this minimization is done in the original 3D Euclidean space where isometry is defined, so no embedding errors. Our output is consistent bijections over all pairs of isometric sets. We closely approximate the exponential optimal solution in a fast way, and we are robust to several problems like non-uniform triangulation and noise, and we do not have any topology restrictions like sphere topology or something. And these are the people involved with this project, myself, and this was basically the last piece of my PhD thesis, which was guided by my cool supervisor, Yemez. I want to thank him one last time. And last but not least, my family.